There's definitely some sex. Yes, I do.
No, I didn't.
Like you got the email.
I was gonna, and I think.
Oh, yeah.
What is with this flag with so blurry?
Oh.
Wow, we both know that. You just know that. Like, you don't know, you could know.
Just 75 better.
All right, guys, page 1.
I got it.
So we're going to start unit 3. And this is not going to be on the quiz, but this is kind of like a continuation from unit 2, because as we talk about chain rule and implicit, a lot of the unit 2 topics are going to it'll build on the previous topics of power rule, all the derivative rules, product, and quotient rule. So the first, so today's topic is chain rule, which deals with how to find the derivative if there's a function within a function, composite functions, like something like f of g of x. And I just want to start off by showing that these are composite functions because there's a outside portion and an inside portion. So in this notation here, my outside function is the f of x, or the f parentheses. And then the inside portion is the g of x. And if we can recognize the inside and outside portions of a function, then the derivative becomes a lot more manageable, because then you can just think of, oh, I'm just going to take the derivative of the outside portion, and then in turn take the derivative of the inside portion. So just want to start off by just identifying these outside inside portions. So sine of x squared, the outside portion would just be the sine without the x squared. Here, the inside portion would just be the x squared. If you see a radical, you can rewrite it. So what's another way that we can rewrite square root of natural log of x? We can have parentheses to the 1/2, natural log inside. So if you think of it as so basically, the outside function is whatever you see outside the parentheses, and the inside function is whatever you see inside the parentheses. So use parentheses as a way of kind of helping separating your outside inside portion. So my outside portion is just that parentheses to the 1/2. And then the inside portion is that natural log of x. This one, if you can recognize this as basically a function within a function within a function. So there's like 3 layers to it. So the outermost portion is just that cosine parentheses. And then the next part in is that sine parentheses. And then the innermost portion is that 5x. So here's chain rule. Chain rule, we have a derivative of a composite function. So derivative of a composite function is the outside derivative. So we see that f in this notation is the outside function. So it's f prime. And when you take the outside derivative, you're not going to do anything with the inside portion. You're just going to have to rewrite it, because we're not ready for that inside portion yet. And then once we get done with the outside derivative and then just recopying that inside portion down, then we're ready for the inside portion's derivative. So then the inside portion's derivative is just g prime of x. So we can say it this way. It's outside's derivative multiplied by the inside's derivative. So the nice thing about chain rule is that now we don't have to expand everything out and rely on just power rule alone. We have more flexibility for more complicated problems. So example one is example here, f of x equals x squared minus 5 to the fourth. This would be a longer process, having to FOIL all this out, right? You got to, it's going to be a longer, can't just distribute the fourth through. We got to write this out 4 times. I mean, we can use Pascal's triangle, but we prefer to not have to expand all this, all this out. On the, for us, all we are responsible for is being able to FOIL out a binomial squared. You're not going to be asked to expand out binomial cube, binomial fourth. We're going to have a better option. And the better option here is, oh, what if we just recognize this as outside portion versus inside portion? And then we can allow chain rule to do that. So let's practice identifying them here. So this is good problem for us to chain rule because we can clearly see there's an outside portion, that parentheses to the fourth, and the inside portion being the x squared minus 5. So let's practice finding the derivative of this function here. So f prime of x is equal to. So outside's derivative, imagine this parentheses as it's like x, like as a variable. And we can just rely on power rule, right? What's the power rule of that portion if we just treat that as an x? 4 parentheses cubed, right? You just applying, letting that x be a kind of like messy parentheses there. So your outside's derivative is just power rule 4 parentheses cubed. And as you do that, you're going to copy that x squared minus 5 in. We're not ready to do the x squared minus 5 derivative just yet. We're not in that portion just yet. Right. So this represents f prime of g of x. We took outside's derivative, but then we just recopied the inside portion and we didn't make any changes to it. Times, now we're ready for the inside's derivative. So times what? Times 2x. So this is a lot more efficient than having to FOIL everything out, combine all the like terms, and then going through power rule for all the many terms that there are, and then merging it all together and factoring it out. We already have something already in factored form a lot more efficiently. So really the only cleanup that I would do is merge the coefficients together. Oops, x squared. Okay, any questions? Number 2, this we can also recognize as a function within a function. How can I rewrite this? Parentheses. Now, parentheses is same as bracket. I sometimes have to use bracket just so I can separate things a little cleaner for myself, but there's no difference between bracket and parentheses. It's just a preference for me. Okay, so try it. You want to try this one here? Identify the outside, identify the inside, take derivative, take turns with each derivative, and see if you can follow this rule and follow what we just did with example 1. So my bracket parentheses is my outside function. So outside's derivative, 1/2 parentheses or bracket to the -1/2. I'm just applying power rule with my exponent. And I'm just treating this mess as its own variable. And as I do that, I'm not making any changes to it because I'm not ready to do this derivative yet. Once I get done with the outside portion, then I can focus on the inside portion. 4x becomes 4. And in terms of cleanup, I'm just going to try to merge the coefficients and then push the expression back down to the denominator. You can leave it the denominator as rational exponent, or you can bring it back in terms of radicals. It's fine. Again, no issues in this course with radicals in the denominator. Number 3, what's a way that we can rewrite this using parentheses or brackets? Or what does this squared mean? Or what's that impacting? All of it, right? So what if we just pull the parentheses or bracket outside sine of 5x? These mean the same thing, but this is the way that you're going to see a problem written because it's a shorthand way of writing it without having to use as many like brackets or parentheses. But this is the form that is more useful for us. It's easier for us to see the outside-inside relationship with the bracket. So I would highly suggest that whenever you see a trig function, always rewrite it. Because if you don't, I mean, it's not wrong if you don't, but it's a lot harder to see that that chain rule relationship if you don't first see all the this separates your outside inside a lot cleaner for your chain rule. Okay. So this is a outside, inside, and inner relationship here. So the outside-most portion is my bracket squared. And then I got to take sine's derivative. And then I got to take 5x's derivative. And they're all going to kind of be nested within each other. So let's do the outside portion first. What's the bracket square's derivative? Yeah, so 2 bracket to the first power, or parentheses. And then what do we put inside here? Sine of 5x, right? We're not going to touch that. We haven't done anything there. Times, okay, so now we're done with the outside portion. We're moving into sine. What's sine's derivative? Cosine. So cosine of parentheses. What goes inside the parentheses? 5, what? X, right? Because we're not ready for that 5x derivative yet. And now 5x's derivative is 5. So that's going to be times 5. So we're just letting each function have their own turn at the derivative. And if there's something inside of it, then we're not going to make it do its process until later. So the only thing I can clean up here is merge the 2 and 5 together to make it 10. Okay, any questions? I do want to point out something about chain rule. Sometimes students have the tendency to want to do too much with chain rule. And what I mean by that is with a problem like this, for instance, right? Number 2, I see some students do this where they find the derivative and they're good with the outside derivative. So they'll bring out the outside derivative. But then they would want to just combine too many things at once, and they just do the inside derivative within the parentheses, and just call that done. So make sure that you follow your derivative rule. It's not f prime of g prime of x. It's f prime, leave the inside alone, and once that's done, then you do the inside derivative. So for a problem like number 3, some students do this. They would bring the 2 down. They will do sine's derivative, which is cosine, and then they'll do 5x derivative, and they'll make it 5, and they'll just nest everything together. And so, well, I did all the derivatives, but it's not the right process. So I just want to point out some of these student tendencies here. All right, number 4. Natural log of x cubed. We can think of it as there's an outside portion, natural log, parentheses, and then my inside portion is my x cubed. So we can take turns with each derivative here. Outside derivative, natural log of parentheses is just 1 over parentheses, right? 1 over x. And I'm going to leave that alone. And then the inside derivative, x cubed becomes 3x squared, which can reduce to be 3 over x. Now, I just want to point out that with the log expression, you can a lot of times apply properties to clean things up. So technically, we can bring that 3 down first using power property. And then this becomes a lot easier to work with because the 3 is a coefficient. Natural log of x becomes 1 over x. So y prime is equal to 3 times 1 over x, which is 3 over x. I think that's what number 5 was for. I was supposed to work it in 2 different ways. One way is expanding first and then take the derivative. The other is jumping into chain rule, which also works. Okay, number 6, we see outside inside portion because of the parentheses. So let's identify the outside portion. Is that parentheses cubed. And then the inside portion. So outside derivative is just power rule, but inside derivative, we got to go through what? Do quotient rule. Okay. So sorry, this should be f of t to match the variable here. F prime of t. So we do outside derivative first, which becomes what? 3 parentheses squared. So 3. We're going to use bracket squared. And then we're just going to recopy everything inside without any changes because we're not ready for that portion yet. Times, and now we got to do a whole quotient rule portion for this. I'm going to have a space reserved for my quotient rule. My derivative of this is going to go in this space. So f prime g minus f g prime all over g squared. F prime. The function, no changes. F function, no changes. G prime. All over denominator squared. This looks like a mess to clean up, but I think really the major cleanup that we're going to do is really just here. Once we clean that up, we can do a little bit more merging, but it'll be a lot easier after that. So I think the hardest part, the most time-consuming part is just trying to get all this cleaned up in terms of distributing, combining like terms. And then once we have that, then I'll show you what the next step is. So I'm just going to distribute that through and see if I can clean that portion up and not have to rewrite all this over again. Here, I'm going to do two things at once. I'm going to distribute the -2 through the t squared plus 1. So I don't have to do the negative and then the 2. I'll just make it a -2 distributed through the t squared plus 1. And this becomes 2t squared minus 10t. Oops, sorry, 2t squared minus 2, not minus 2t. So this is my cleaned up version of this expression. So I'm going to try to put it all together under one fraction. So my numerator is going to be the 3, the t squared plus 1 squared, and the 2t squared minus 10t minus 2. And my denominator is just a bunch of 2t minus 5. How many 2t minus 5s do I have in the denominator? Okay, it looks like 3, but there's actually more. 4. Why is it 4 and not 3? Okay, so just another thing to be aware of. I think a lot of us look at that 2 and we see it for the t squared plus 1, but we don't quite see it for the 2t minus 5 because it's so far away. And so we always want to check that number here. That 2 is impacting both the numerator and denominator. So a lot of students look at that and they see, oh, there's only 1 here, there's 2 here, and I'll make it 3. 1 plus 2 is 3, but just be aware that that exponent, I know the distance is kind of far, but we have to make sure that 2 is impacting that 2t minus 5 as well. So there's 2 here, there's 2 here, and that's going to give me a total of 4. Page 2. Okay. Top of page 2, number 7. This is also one that we can rewrite because we see a set of a radical there. So let's rewrite this as g of x equals 2x and then parentheses 1 minus x to the 1/2. Now there's chain rule within this 1 minus x to the 1/2 because there's an outside portion and inside portion, but this is actually a little bit more. There's also what involved here? Product rule. Because we need to think of this as, oh, this 2x is separate from this parentheses and they're being multiplied, and I'm trying to find the derivative. They're not easily compatible. They have to stay separate. And if I want to find the derivative of two terms that are being multiplied, I'm going to have to go through the product rule. And some students would ask, wait, how do I know which one to do first? Am I going to do product rule first, or am I going to do chain rule first? The general rule of thumb is you want to apply the rule that has a larger impact first. Okay, so if you're deciding between two rules, apply the rule with the larger impact. So here, product rule is impacting a larger portion of the problem than chain rule. So you want to do the larger one first. Okay. Here's another way to think about it. You look at your parentheses. If your parentheses is over everything, like number 6, then chain rule is going to come first. If your parentheses is only over a portion of the problem, then it's the other rule that's going to come first. So in this case, parentheses is not over everything. So we know the other rule has a larger impact. So product rule is going to be applied first. And then within product rule, then when we get to G prime, will involve chain rule. Okay, so let me set up G prime. F prime G plus F G prime. So 2x becomes what? 2. G, no changes. Back to F, no changes. And G prime is where we got to involve chain rule, right? So within G prime, there's an outside portion. And then the inside portion. And then we take turns with each derivative, and all that's going to go into space here. So outside derivative, parentheses to the 1/2 becomes 1/2 to the negative 1/2. Keep the 1 minus x alone. And then times the inside derivative, 1 minus x becomes what? Times, what's 1 minus x derivative? -1, yeah. So my ultimate goal is to find G prime of -3. So I'm going to do a little bit of cleanup, and then I'll just plug in -3 in. So not going to do too much here. Just want to do a little bit of combining. I realize the 2 and the 1/2 can cancel out. I'm going to push the negative out in front with the x, and I'm going to push this negative exponent back down to the denominator. So again, 2's cancel out, parentheses comes down, and I can merge the x and -1 together to make it minus x. So now it's relatively cleaned up. I don't need common denominator. I can just plug -3 directly in for x and just see what that gives me. I get 2√4. Number 8. Any questions so far? Number 8, we have the need for chain rule for all these functions, but now these are in function notation. So let me just rewrite it with so I can see the chain rule need. I can do bracket parentheses to the one bracket to the 1/2. So f prime bracket to the 1/2 bracket squared. I can go through power rule there. Outside portion is 2 bracket to the first power times the inside derivative. So g of x becomes g prime. And now I can, once I have my derivative spelled out, I can replace every x with 4. So I can move towards f prime 4. And then you use your table of values to make your substitution, replacing all the function notation with numeric values. G of 4 gets replaced with 3, and g prime of 4 gets replaced with -2. Right, try part B. Outside is my bracket to the 1/2. Inside is my h of x. I'm going to take turns with each derivative. Replace every x with 4. H of 4 is 9. H prime of 4 is 5. If I push that 9 down to the denominator, I get square root of 9 is 3, but 3 is in the denominator there. Part C, we filled out our derivative. There's a need for chain rule. There's an outside inside that we see. Outside's portion is that h. So h's derivative is just h prime. Keep the inside intact. Times what? Times g prime. So first things first, we're going to replace every x with 4. Now, just be aware that this is a multi-step process. We're not going to be able to just plug in and just find this numeric value all at once. So do the part that feels manageable first, right? This is a lot to do, G prime, H prime of G of 4, but we should be able to find G of 4 and G prime of 4 relatively easily. And then once we have that, then we'll substitute, and then we should be able to have an easier problem in front of us. So G of 4 gets replaced with -2. But as I find things, I want to make sure that I still have my unresolved portions in my problem. So now it becomes a lot cleaner because we know G of 4 is 3. So now we're down to H prime of 3 times G prime of 4. And now this, we can just pull the rest from our table. H prime of 3 is -3, and G prime of 4 is -2. All right, I want to spend the last 10 minutes or so just reviewing the limit definition of a derivative and what we need to know about it for the quiz. So if you want to put this down on a separate sheet of paper, let me start going over this here. Okay, so there's two definitions here. The first is general definition. We need to make sure we memorize this. And we need to know this in two ways. One way is, can you work it out from beginning to end and get to the derivative? And these will be pretty easy in terms of power rule. You just go through power rule and you know your answer is already going to be 2x plus 3. You just want to show all the work to get to that point. So let's say I want to find f prime if the function of x squared plus 3x. The first thing we want to do is put this into the definition. So every x we see replaced with x plus h. That will go in this slot minus the original f of x function. So this is how we interpret that x, or convert that x squared plus 3x minus 1 into f of x plus h. Every x gets replaced with x plus h. That's my f of x plus h minus f of x. F of x is the original expression, all over h. And now you're just expanding everything out. You know that you can factor an h from the numerator because this gives you 0 over 0. But when everything is said and done, you'll be able to factor an h out. And then combining like terms, you reevaluate after you combine like terms and cancel out, you reevaluate, replace every h with 0, and just like what you expect, the derivative is going to come out to be 2x plus 3. Right. And if I ask you what is f prime of 2, then that's easier. Let's just plug in 2 into the derivative to get 7, and that's your slope. What if I just gave this to you? What if this was the starting point? Are you able to see that this is coming from the function x squared plus 3x minus 1? Okay, so the highlight is, if this was here, that would be nice, but this is also an indication of finding it, right? I mean, I know we see it here, but imagine this wasn't here. We should be able to spot it from here, right? My parentheses is my x, so x squared plus 3x minus 1. Now, what if I wanted to represent this as finding f prime of 2? Then it could maybe start off like this. Imagine this is your starting point. First off, can you pick, well, first off, we know that this is a limit definition. This is asking for the derivative of something. Can we tell that the function is x squared plus 3x minus 1? Yeah, so this 9 is not going to do, it's not going to help us, but this should be enough for us to pick out, okay, that's, if I strip away all my parentheses, replace with x, there's my x squared plus 3x minus 1. And can we tell that this is asking for find f prime of 2? Yes, right, there's the x has been replaced with 2. And so if we can look at that and know that it's asking for this, given the function, then we can just ignore that and just rely on power rule, plug in 2 and get to our answer a lot faster, right? So this is more of a, can you interpret what this is asking? And then once you get to what you know they're asking, then there's no need for that limit notation. You can just use power rule and plug in 2 to get to it. So just being able to recognize that. Let me also go over the alternate definition. And let me do that one from scratch. We also need to memorize the definition limit for the alt definition. And it's this one here. F prime of C is equal to limit as x approaches C, f of x minus f of c all over x minus c. So if I were to ask you find f prime of 2 given the function, we're just going to go through, let's build it from scratch, find the derivative from scratch. So replace every c with 2. So replace every c with 2. And then you can go ahead and start to get the numerators out of function notation. Replace f of x with x squared plus 3x. Replace f of 2, plug 2 in to get tanh. And then once you have this, then it becomes the limit problem. For our substitution, we get 0 over 0. We can factor, reduce, reevaluate, and it takes us directly to our slope, which is f prime 2 equals 7. So this is if we were to work this out from scratch. But if this was what was given to us, just this portion, and we recognize that, oh, this is talking about x squared plus 3x, and it's asking for me to find f prime of 2. So this one I think is easier spot because that first portion is going to be your function, and then the c value is going to be the number that you're trying to find the derivative of. So if you can understand this x squared plus 3x, my derivative is trying to find f prime 2. Again, I'm just backing power rule and plugging 2 in to get to my slope. So that's what we need to know with limit definition. Either you're finding the derivative from scratch for an easy power rule problem, or you're having to look at a problem halfway finished and be able to pull out what information or what they're asking for you to find. Okay, so your homework, I'm going to make an adjustment here. So the calendar says page 1 through 7 all. I'm going to make it page 1 through 4 all. I'll send out a reminder this afternoon from your chain rule. Question number.
So you think you're gonna not be down? I got a little confused. You did, but that was. No, really, on the outside, no change. It goes back, it goes back, then you take 2x. So you're going at 5, and then, yeah, outside portion. Yeah, but number 4 inside. That belongs to the side. So, R minus 2 over 1 over parentheses. Square minus 2 plus 1.
Place that with X. And then. Yes. Have a good day, guys. See you tomorrow. Bye. Thank you. Yes, from yesterday, fish 3 and 4. 3 and 4 for the quiz.
You mind going back to
Sure.
I think so. Negative 1. So funny. You extend it. I'm just gonna be, yeah.
Oh, sorry. This function is just extra plus 3.
Thank you.
Yeah, I mean, this is from the general definition.
Yeah. So, but the,
This one, I started off with S actually.
oh, okay.
3.
And 4. Oh, I didn't say.
Okay. That's fine.
Yeah, that's a good.
Okay, great. All right, thank you.
Good man. I'm gonna study very diligently. I should make all the whole packet.
You can do the whole packet.
Yeah.
Yeah, the quiz.
So should I just like send it again? We did it. It sounds like.
Yeah, or have another copy. Okay. But do you have anything that is the one you want? Steps?
Not really.
Then, just be aware, this was
That was definitely.
yeah, but as long as you know the starting point, set the equation equal, set the variables equal, replace all the x values forward. And just be aware that a's and b's are coefficients, that they're numeric values. So for instance, let's say I gave you y is equal to 3ax squared plus x plus 5 a y a b, all the derivatives.
Let me just be like.
Might not be, because the one going x.
Oh, yeah, because the 1, 6ax, and then plus like 4. And then plus 5, no, just plus 8. So, oh, because the code.
So yeah, so keep reminding yourself that
Yeah, that was confusing.
a's and b's are just numbers, and it's the x's that's a variable. So
Okay.
the power rule, that you're not getting thrown off by that.
Oh,
So yeah, do that again.
All right.
Okay. That's fine.
That's actually what. Ask a question. There's no.
Just,
Okay, sorry.
yeah, this one is not like you're just comparing.
Okay. Yeah, 8 4. I got And then just take notes and maybe
It should be scored at 8.
Okay, great. Okay, and just keep stopping. Those fine, those like. Great. I don't know about the end. And also a little bit. What? A little bit. Oh, a little bit.
But these are literally the ones that-
I was at a doctor. I texted Duncan. Yeah.
And there you go. Was it pretty good though?
Gotta go. Yeah. That was it. I was like watching.
Or was that?
I'm gonna come around and check your pages 1 through 12 again, just the ones that we did in class. So as I'm doing that, if you guys can start page 13. I'm just gonna pick up your packet. I'm just gonna just flip through it so that you don't have to flip through all the pages. But go ahead and start page 13 as I walk around.
What do you normally choose?
Still not as great. I know you. Maybe I would think it would. Let's say look.
I shoot like 80. I got there from 80. I got that. I shoot 80 every time. I shoot it. It doesn't go up. Like 90.
Nope. Brown, rather go to.
Yeah, I know. Well, it's all everything. I know. Capital City shut down. So when you see it, they're like carrying it up. And I used to Capital City.
Wow, right.
I used to close just because.
When did they open back up after the thing?
I don't know, because I know they're doing some other like memorial tournament right now. Guy died, melted, starting that, and then they have to take down all this stuff, so probably this upon, yeah.
My brother.
That's all right, just tell your dad to like remind you.
My brother had flew over.
Well, actually, yeah, that's.
Flew over a couple of hours, right?
Yeah, that was all.
Like, so yeah, I didn't hear.
Wait, when's that?
No, not for a year.
Really?
They're building you, they're building the halfway house and everything.
From.
Okay, sorry. Yes.
You took pop over. So it's down. Oh, great. Yeah, probably. You're just gonna. I don't know, but I'm very sorry. What are you doing? Leave like three students on clock. Yeah, the features, we told them to skip that. Are you taking online classes? Yeah. You have to miss the additional last time. But
Yeah.
I'm like, I want to grind get that.
Yeah.
I'm looking like they want to do this. Got out like this.
Where do you take it?
Hey, the first one part. First of all. Environmental science. I'm halfway through culture. Halfway through. There's, I feel like 11 A's. I don't remember it. There's only like a 4 for the science.
It should be. When you read these, it feels like, what's it speaking? And it was like, if we just add additional. You don't want to be adding.
I make my squares and shorts.
What they did, my. Last year, I had like those.
Right, like, I don't care. Yeah, me too, but it's cool. Like, I don't care, like,
Yeah.
great, like, how much food? Yeah. Yeah. What are they at?
No, I was.
What are they at?
They should just make questions. Then my teacher just asked if that's it or something.
Alright, let's pray for them. Yeah.
All right, so page 13, the top half, the top portion, you're just reading the graph and pulling the values. Remember, limit, we're looking at the approach not necessarily what's happening at that point. So you want to pick points close and draw arrows and see if there's an agreement. Part 1B, you're walking through your continuity conditions and proving whether there is discontinuity or not. And then if there is, to be able to confirm that it is jump or removable or non-removable based off of where the conditions fail. And you don't have to say this not equal. So you jump directly from bounding limits, one side limits, and then these are obviously not the same, so therefore you just say limit doesn't exist. Okay, any questions? Page 13. 14, the it's one of those strange graphs, but this is a little messy with the exponents. I'm just gonna, if I give you one, it'll just be, let me change this one. It'll just be square root. It won't be anything dealing with cube root. So let's do this one here. Right. You don't have to, you can, but again, this course, you don't have, you can leave radicals in the denominator and you'll be perfectly fine. We understand that degrees are the same. We're doing n behavior. Our limit is showing us -4/√5. But because of the radical, it's going to always stay positive, or because the square is also staying positive. And so when it goes the other direction, it's going to change this sign, and that's going to cause there to be two horizontal asymptotes. Make sure that you specify y equals. Otherwise, if you just say the limit, then that's not true asymptote lines. You gotta say y equals. This one. Plus or minus. Sure, yeah. Or you can say, yeah, or you can do this, y is equal to plus or minus 4/√5. That's fine as well. That's indicating that there are two lines there. So. All right, number 4, A and B, you're stepping through your continuity conditions. And see if it passes all three, or if it fails if it fails 2 or 3, you can stop and indicate what type of discontinuity it is. I messed up my key here. It should be, you got 11 here. Part B, that doesn't equal to mean only one limit statement needed.
When you got 11, how do you know that it's just, you're not multiplying the -2 by the -4 and like to hold that, like, just the 2 times -4? Yeah.
You guys not get 11?
No, I did get 11.
Okay.
I was just curious.
So we always do direct substitution first, right? -4 in for x. So negative times negative is positive, and 8 plus 3 is 11.
Oh, okay.
Yeah, I made a mistake on my key. I think I read that as +4, and that made my answer -5 on my key.
You say like continuous at like all points for all,
Remember, we're only testing for -2.
for, oh, right.
So remember, anytime you have a continuity or discontinuity, it's only at a single point. We're not saying anywhere else. So all we can say is is continuous at -2.
Okay.
So this is, we've done so many where things don't pass. This is one that does pass all three conditions. Order pair is -4. There's a hole at -4 as well. That they're getting filled in, and so all three conditions pass. Okay, try number 5. Now I'll work out each problem on the separate sheet. I think I just wrote the answers down. I didn't show the work for a lot of these.
For E, wouldn't plugging in -1 for T, -1 minus 1.
Well, this -1 goes in for this t. So it'd be 1 squared minus negative. So two negatives cancel out.
When we test we test the 0.1 or the -0.1 last one, because it's a vertical asymptote. We don't ever look at like degree on that, do we?
No.
Okay,
When do we look at, when do we?
if it goes toward infinity
That's right.
or negative.
You only compare degrees to this one to infinity. If it's putting a real number, you always plug in that number. Okay, any questions? Okay, if you haven't done page 17, go ahead and go through page 17, another piecewise function where you're just trying to nail down that first step, right? It's either direct substitution or it's compare degrees. We don't want to jump steps. Any questions on page 17? Did we go through page 18 together? We did, right? Okay, so let's see, bottom of page 18, there's some empty space there. You can call that number 4. Let me guess, have you tried this one? You're gonna use continuity condition as a problem solving tool. So bottom of page 18. Copy that one down, number 4. So number 4 is a problem solving tool, using limit continuity conditions as a problem solving tool. Find your order pair, set up your limit. You need one-sided limits. And once you get to that stage, you should be able to get enough information where you can solve, set both sides equal and solve. I think in the back of your packet, there's some empty space. Try this one as well. This is also one where you're solving for a missing k value. Go through continuity conditions, but with the radicals involved, you may have to use your conjugate method.
Do we expect this? I mean, that's.
Yeah, you're just walking through continuity conditions, solving for k. If it's this form, you know you need 2 one-sided limit. This form, all you need is one limit statement plan.
This year,
Mhm.
after this one, can we go to IVT ones?
Yeah, I'll do an IVT after this one. Yeah. It's 2x plus 5. All that is to show that the limit does exist at 110. So we keep going. We haven't solved for k yet, but we're almost there. Third condition, we need these to agree. So the point has to live where the limit lives. And so we can force k to be equal to 110. Let me do an IVT problem here.
There was a hole and it wasn't continuous or a horizontal asymptote or a vertical asymptote after we found that. Would you just stop there instead?
If that hole is interfering, if the hole is between 0 and 3,
Just say.
yeah. But again, you don't have to worry about whether it's a hole or a vertical asymptote. You just set the denominator equal to 0 and whatever you find is a discontinuity.
But if there's a discontinuity, there's no IVT.
Yes, if there's discontinuity inside the interval, then IVT doesn't apply. So this function is not
X
continuous. Right, yeah. Let's say there's a divided by x plus 1, or sorry, x minus 1. If there's an asymptote or a hole at 1, then you would say by IVT, the function is not continuous from 0 to 3, therefore IVT doesn't apply, and you would stop it.
What if, even if, say that exact function right there was over X minus 1.
Okay.
Would there be a discontinuity?
Over x minus 1, yes, there'll be discontinuity at x equals 1.
And
And 1 interferes with the interval, so IVT falls apart.
even though that would look factor into -4 and x equals -4, or x minus 4 and x minus 2 over x minus 1, right? But it'd still be a discontinuity.
Exactly, yeah. If it cancels out, it's a discontinuity. If it doesn't cancel out, it's still a discontinuity because the hole and the asymptotes are both discontinuities. We don't have to differentiate between the two of them.
Thank you.
Um, like, since the whole statement.
Yeah.
Are there different ways we could phrase that?
Yes. I think the reason that I do it this way is this is the most efficient way. It gets all the information across. You're showing that your target is between these two y values, and then these two y values are coming from the endpoints. But if you split it into different statements, that's fine, as long as you have all that information presented to you. What did you have?
That-
That works. All right, how do we do part B? How do we find C? Good. We just set that equal to 0, solve for x. And what do we want when we solve for x? Yeah, something between 0 and 3. Right? If something is outside of 0 and 3, you got to remove it. What if both are outside the interval? That means we did something wrong because from part A, we've already guaranteed it. So we have to find at least one solution. So if you can't find a solution in between, go back and redo your work because by the end of part A, we've already guaranteed it. So there must be a C value. Hey, any questions?
Is it possible you get two answers if they're both in the same interval?
That's true. Yeah. Sometimes it's possible to get both answers inside the interval. If they do, then you'll keep them. But you're guaranteed at least one. Okay, so help session tomorrow morning. And help session tomorrow morning, I'm going to just go through pages 21 and 22. And then if we have additional time, then I'll just create more problems for us to do in help session. I'll send out a reminder this afternoon. I'll send out a reminder tomorrow morning. If you want to join virtually to the help session, you can. But you can also work on page 21 and 22 on your own as a way of kind of like as a mock test for yourself to see, how it would feel. If you want additional practice, go back through the test review packet, but also through your notes packet, because there's a bunch of problems that we have skipped over. You guys have the keys for that. You guys can check your answers. But yeah, no calculators tomorrow. And hopefully you guys feel pretty good. Yeah, so help session tomorrow at 7:15.